Hello, today the session will be about BMX in Creo. The task today is we're going to determine the volume of a bottle, and this one is a solid bottle. I'm going to share this bottle here, like that, and I'm going to determine this volume at a certain level. I'll use a plane, maybe I want this volume. Just use a plan as let me section view here. Maybe I want to know what's the volume of this bottle. Assuming we have a liquid inside here. The assumption is there's a liquid there. I want to see what is the volume there. Okay. Therefore, let's see how you can perform that type of analysis in Creo. Okay, I'm going to go back like that. This is my bottle. For now, is a solid. We are going to shell it. Therefore, what you're going to do is we're going to find volume of this solid, then we are going to subtract volume of the shell to get the volume of the fluid. What do I mean? This is solid. We are going to shell this like that. Then you're going to find this volume. Once you subtract those two volumes, you're going to get the volume of the liquid or the volume of the air in the bottle. Therefore, let me just go back here. We need now first to determine the volume, but I need to know the height. Maybe and I'll assume that I'm going to assume that the shell here is 2 mm thickness. Therefore, I need to create a plane at 2 mm. And this plane, the property is the bottom plane. Why am I using 2 mm here on the placement? Because we have a shell. Once we shell with 2 mm, the bottom of the fluid will be at 2 mm from the bottom plane. Therefore, if I go front view, when you shell this one here, the liquid will start from here, like that. Let me just change the display. We can change the display. Let me just go to top view. Can make this plane bigger a little bit, just for you to visualize. And I can hide. Let me just hide these planes. I need another plane here. Now this is the height of the liquid. You can say liquid height. I'm assuming the height is the liquid is at a certain height. Let's start with 100 and see the liquid present there. Again, let's go to the top view, and I want to use the size of this plane to make these two planes same size. Therefore, we want to determine the volume between these two planes of this bottle. Therefore, the first thing I need to do is determine the volume of the solid here. I'll go to analysis. I can use two methods. I can use mass properties or I can use measure volume. If I use mass properties option, here you need to select the quick body or solid. For now, I'm going to use a solid geometry. When you preview, you get volume here, you get surface area, density, mass, center of gravity. For you to use this method of mass properties, you must assign your model some material. You right click here, edit materials, legacy, can use any, maybe PVC. Okay, therefore, for you to use mass properties, still can use this method here of volume as well, like that, to to 2196, but let me use the mass properties method of the solid geometry preview. You can see the same value 2196, but this one returns the full volume of the bottle, but I need from this plane. Therefore you can select the plane here. When you go to, I can say preview here, then I think on this method you cannot use the plane. I think you cannot use the plane. Let me see here. When it says quick, you can say feature. For the coordinate system, you can select the default one here. But here you can't use the mass property method because this one returns the full volume of your solid, and this one returns all the parameters. But for me, I need the volume between these two planes here. Therefore, let's use the other method of the volume. Because this volume, you can select a plane. You can see you're getting the same value, but this method can select this plane here and use that plane. You can see this plane, this volume is facing up, but I want it to face downward, face that direction there. This means this arrow, it determines the volume from this plane is at bottom or up. I want to determine the volume in this direction here. Okay, therefore this value is the volume from this plane to this plane. When you go to this sphere, I want to do regenerate all the time. Once I change a dimension, I have to regenerate. But we can also use read only, or we can use design study. Let me use always generate. And here I want to use the word, I want to give them a name. Volume. This one is volume. When I do make feature, I can say pre-shell volume, like that, or pre-shell vol, like that. Then you can close. Now you have this volume here, 776547. This is a pre-shell. Therefore, if you change this plane, this volume will change. For example, if I go more higher, you can see 101. Because I said regenerate here. When you go here, you said regenerate always. What about when I say read only? When you say read only, let's see what happens. Change this. The volume doesn't change because I'm saying is a read only value, but for me I need this one to be to regenerate, to recalculate the volume. Then you shell. This one here we are shelling by 2 mm. You see there's a 2 mm because our bottom plane here was 2 mm. Therefore 2 mm shell, like that. When you shell, let's do a section view onto this plane here. You see now we have this a shell. Before shell, we are getting this volume. This is a pre-shell volume. When you shell, now you're getting another volume here. Let's calculate this volume of this solid. This volume should be smaller than the pre-shell volume. If you go back to now analysis, select volume. See now onto this plane again. Here, this plane, bottom side. Here we said this is a volume. Always regenerate. We are going to do post shell underscore volume, like that. Cross. Now you have two volumes. One is pre-shell and one is post-shell. Therefore, if you take pre-shell volume, call it P1. If you subtract post-shell volume, that is called P2, you're going to get the volume of your fluid here. It's a volume, it's a fluid here. When you subtract, therefore, We're going to take this volume here and we are going to subtract this volume. Okay, therefore we're going to create a relation. For you to do this type of mathematics, you need a relation. You go to the analysis here. Therefore just need to go to this analysis tab, then you select this analysis here. Okay, therefore analysis, we get analysis. There are 6 of them. We have a UDA. UDA is called user defined analysis. There's a video I've created for this. Excel analysis, I'll do that later. External analysis, economics analysis, Creo simulate, I'll do this as well. But you're going to do a relation. A relation is when you relate to parameters. Maybe you want to subtract them, you want to add, you perform what we call relation analysis. Therefore, when you select relation here, you can say volume of fluid. Can give a name like that. And when you say next here, you open up this one here. Here is where you write your relation. Therefore, here is you write relation here. And the relation we're going to use, it is for the parameters. Therefore, this one means parameters. Here, insert parameter name from list. Therefore, the parameter name is volume. I can say my parameter name is a volume. Remember the value of the volume, the one I wrote here. I'm going to say volume equals, you select parameter, then you look in feature here, you select pre, you can see name is volume. Let's click here, select this one here and say insert selected. You can see volume FID 601. This FID is this feature ID is using 601. This is the 601 here. You can see here 601 to this one is the volume we are using here. Therefore, minus, you can still type volume like that, FID post shell, that is a 616. You can say 616. You can also type the relation. When you say verify, relations have been successfully verified. You can say, yeah. Still, you can use, instead of writing FID 616, you can still write the name. You can say post shell volume. When you verify, still relation has been verified successfully. When you say okay, and you say okay, you get your volume of fluid here. When you take this and subtract this, you get this. This one is subtraction. When you try to change this height, this volume are changing. I can see now we have 911,622. I want this one to be exactly 1 million. Let's see how to get 1 million. And that's 129. It's very difficult for you to know the exact value that will give you 1 million, but we can do that using sensitivity analysis here. You can see sensitivity analysis and what we call feasibility stroke optimization. We're going to perform feasibility, but first let's perform sensitivity analysis. And you want to see when you change this value from 100 maybe to 200, and can this volume of fluid, let's see the volume of fluid, how it will change. Okay, now I see that when I change the value of my plane from 100 to 200, the volume increases using linear, increases in a linear way. Therefore, I want to get this volume here, 1 million, and I want to see, and I can say it is 140, but maybe it is not exact 140. Yeah, it is not exact 140, but I want to know the exact value here from this value exactly that gives a volume of 1 million. It is between, now I can assume it is between 135. I can take 135 lower side and upper side 145. I can do that. Therefore, let me just cancel this. I can do what we call feasibility analysis between this dimension here. I can change this dimension from 135 to 145 like that. Let's see, is it feasible to make this volume here, this volume, the fluid, to set it, to make it 1 million. 1 million. If the convergence error is 0.0001, maybe I don't want to get a very big error, because sometimes you might not get an exact 1 million volume. And I want to see what happens to the constraint variables. Constraint is this, because we are saying from 135 to 145, that becomes constraint. Variable is what is going to change. In this scenario, my volume parameter is my variable here. When you say compute, I can see the optimization limit convergence graph is it performed 2 iterations. First iteration, second iteration to confirm 1 to 2, and it got the volume. You can see we got our volume here. Let's see this other graph. My graph initially is 145. It got volume. You can see the volume is between 140 and 141, somewhere here, this value. Let's see that the exact value cross. Now you can decide to set your plane on your plane to be exact value that the Creo found and confirm. Therefore, you can see my volume here is not exact. Remember the error we said? We're getting 99999, but when you round off, this becomes 1M. I can go back again here, and these options, preferences here, I can add another 0, make it reduce error. When you say compute, we now cross this one here, close. Now we are getting exactly, you can see here, volume of liquid here is exactly 1M. Therefore, you see our plane is this liquid height. Let me see the value, 140.81. When this is 140.81, the volume is here is this value. Okay, you can now try and see. When you select this volume, is you're getting 1913. Yeah, you have to do that math. You have to take the initial volume minus final volume. Now you're just getting 7 here. Shell volume. That's how you can use measure mass properties and sensitivity stroke optimization analysis to determine the volume. Yeah, in my next videos, I'm going now to go into the detail of I'm going to discuss what we call Excel analysis, UDA, user defined analysis, this one here, or you can find it here as a UDA, Excel, Creo Simulate. I will discuss most of them for you to understand how you can use Creo BMX, behavioral modeling analysis. Thank you so much and stay tuned for more videos. Bye.